Welcome to today's Explainer. If you're managing technical projects or overseeing device security, keeping your system's core protected is absolutely priority number one. But what happens when the digital equivalent of a janitor's key can be used to completely hijack your most secure vault? Today, we're unpacking a really fascinating vulnerability discovered by Jan Horn over at Google Project Zero. It's essentially a digital heist targeting Android's core, and honestly, the way it works is as brilliant as it is terrifying. Okay, let's dive into this. To make sure we extract the absolute most value from this report, we're breaking it down into 5 sections: accessing the core system, the missing safety check, weaponizing shell access, threat to system stability, and finally, how to fix it. Section 1. Accessing the core system. All right, to really understand this vulnerability, we need to establish our baseline vocabulary. First up, we've got shell access. Just think of this as a very basic, low-security command line doorway. It's the kind of access a developer or a diagnostic tool might use. Then we have the system server. This is literally the core brain, or the central vault of the Android operating system. It manages everything important. So the whole crux of our heist today is understanding how a low-level user with mere shell access is trying to break into the most important room in the entire building, that system server. Now, what's really interesting about this slide is the sheer contrast. Normally, shell access is intentionally limited, right? You run basic commands, do some safe diagnostics, interact with a few apps, and that's kind of it. It's safe. But in exploited shell access, that completely flips the script. This vulnerability allows that severely limited access to hijack the system server entirely, giving an attacker total, unchecked control over the device's core brain. Section 2. The missing safety check. So how exactly does a basic command prompt bypass master control? Well, it all comes down to an architectural flaw. Whenever a program runs, it uses something called a stack for its working memory. Imagine this as an actual stack of temporary work orders sitting on a desk. As the system gets busier, that stack grows downwards. Now, to prevent the system from knocking over the desk and spilling work orders everywhere, engineers place a guard page at the bottom of the stack. In Android, this is typically a 16 kilobyte safety net. If the stack of work orders hits this guard page, the system essentially goes, whoa, okay, that's too much, and it safely stops, preventing memory overflows. It's an absolutely critical safety net. But the attacker in this Project Zero report found a remarkably clever bypass. It's basically a 3-step playbook. Step 1, they distract the system with endless nested requests. By abusing synchronous binder RPC calls, using shell commands like dump heap to trigger callbacks, they push that stack of work orders deeper and deeper, right to the very edge of the safety net. Step 2, right at that edge, they call a specific system function that demands a massive chunk of memory all at once. In this case, a 128 kilobyte allocation. Step 3, because that massive 128 kilobyte demand is so much larger than the 16 kilobyte safety net, the stack literally jumps right over the guard page entirely. It lands in unrelated, unprotected memory, and the safety net never even knew it was breached. Section 3. Weaponizing shell access. Bypassing the safety net is a great trick for sure, but it's not a full heist until you actually steal the control room. Once the attacker has forced the system to jump past that guard page, they're basically operating in the system's unmonitored basement. But they still need the system to execute their code. To do this, they use a technique called a shared memory spray. They flood this basement area with malicious instructions. And here is the genius part. To get these instructions into memory, they disguise them inside standard image files, Android bitmaps. So instead of seeing malicious code, the system thinks it's just looking at harmless pictures of cats or app icons. The attackers copy these disguised files over and over, filling the memory space below the stack, just waiting for the core brain to accidentally read them. Because the stack has bypassed the safety net and is now overlapping with this flooded basement of malicious bitmaps, the system_server inevitably pulls a work order from what it thinks is its own safe memory. But instead, it reads the attacker's malicious blueprint. The exact moment it reads that instruction, the control flow is hijacked. The heist succeeds. The attacker now holds the keys to the security camera room, the vault, the whole shebang. Section 4. Threat to system stability. If you are managing device reliability or operational risk, this is where you really need to pay attention. So the crucial point is, this attack is not a smooth, silent operation. The success rate for jumping the guard page and hitting the exact right memory address is incredibly low. According to the researcher, an attempt only has about a 5 to 10% chance of actually working. It's a highly unpredictable, messy process. Because this exploit is so brittle, what happens the other 90 to 95% of the time when it fails? Well, the system_server crashes. Completely. To actually pull off this heist, the attacker must repeatedly crash the device's core brain. They are literally breaking the system over and over, forcing it to reboot, just hoping that on the next attempt, the memory lines up perfectly. And unfortunately, it gets worse for the end user. Android actually has a built-in failsafe called Rescue Party, which is designed to stop boot loops by resetting the device if it crashes too many times too quickly. To avoid triggering this, the attacker's script intentionally waits 60 seconds between each targeted crash. Imagine the operational nightmare here. A user's device could just sit there, locking up and crashing every minute, trapped in a loop for an hour or more while the attacker plays trial and error with the system's memory. This turns a complex security flaw into an immediate, massive stability crisis for your users. Section 5. How to fix it. All right, we've seen the mechanics of the heist and the operational nightmare it causes. Let's talk solutions. When a Google Project Zero researcher gives you a direct recommendation, you take it straight to your engineering leads. Jan Horn states clearly, I strongly recommend that you fix the core issue by enabling F-stack check for any native code in Android. This compiler flag right here is the ultimate fix. It ensures that the system actually probes the stack as it grows, making it mathematically impossible to simply jump over the guard page, no matter how large the memory demand is. And this brilliantly illustrates the multi-layered defense strategy required in modern architecture. While enabling the F-stack check compiler flag is step 1 and fixes the core vulnerability, a robust defense just doesn't stop there. Step 2 is to limit the maximum stack depth for those nested binder transactions. Basically, don't let an attacker stack an endless pile of work orders in the first place. And finally, step 3, restrict what shell access can actually touch. Rather than letting shell access talk to almost any service by default, move to an allow list model. Only let it touch the specific diagnostic services it absolutely needs. We've seen how an attacker can take a basic, low-level shell access, use it to bypass safety nets, weaponize memory using disguised image files, and repeatedly crash a device until they fully own its core brain. It's a really stark reminder that in complex systems, there are no purely low-risk entry points. So I'll leave you with this to ponder with your teams. If a seemingly harmless shell access can crash and conquer your core system, what other low-level doorways are currently hiding in your architecture, just waiting for the right digital heist? Thanks so much for joining me on this explainer, and keep learning.